When you look at a massive chemical plant, what do you actually see? You see these giant, towering structures, right? Miles and miles of complex piping, huge storage tanks. It's a lot of heavy metal. But what you don't see is the high-stakes, invisible conductor that's actually keeping that entire operation safe, profitable, and environmentally friendly. That invisible conductor is instrumentation and process control. And honestly, getting a grip on this is absolutely the foundation of your career in industrial engineering. So, welcome to the Explainer. Okay, let's dive into this. Here is our game plan for today. We're going to start with why process control matters, then move into the meaning of measurement, direct versus indirect measurement, the elements of an instrument, and finally, wrap it all up with the big picture. Section 1. Why process control matters. Picture a highly volatile chemical processing facility, and it is just operating at maximum capacity. It begs a very serious question, doesn't it? What actually keeps a plant like that from just spiraling into total chaos? I mean, think about it. You've got exothermic reactions generating immense amounts of heat. You've got toxic chemicals flowing under insanely high pressure, highly combustible materials everywhere. Without a system to constantly monitor and adjust those conditions, chaos isn't just a possibility. It is a literal certainty. Now, what's really interesting here is breaking down the 5 primary incentives for process control. First, and absolutely most importantly, is safety. We have to prevent explosive mixtures, period. Second is production specifications, making sure we hit exactly 99.5% purity, for example. Third, environmental regulations, ensuring our effluents and emissions stay strictly within legal limits. Fourth, operational constraints, like making sure a pump maintains a net positive suction head so it doesn't just run dry and destroy itself. And finally, economics, maximizing our profit by using raw materials and energy as efficiently as possible. If all of that sounds a little overwhelming, let's bring it back to something familiar. Just think about driving your car on the highway. Process control is exactly like your cruise control. The whole purpose of cruise control is to maintain the speed of your vehicle, which in engineering terms we call the controlled variable, at a desired value, which we call the set point. When your car hits a hill, the cruise control automatically senses that drop in speed and manipulates the throttle to get you right back to your set point. Well, a chemical plant does the exact same thing. It's just on a much larger, way more complex scale, dealing with variables like temperature, pressure, and flow rate instead of miles per hour. Section 2. The meaning of measurement. So the crucial point is this. To actually control a massive industrial process, we first need a specific language to even understand what's happening. And that logic is captured perfectly by this fundamental rule. Before a condition can be controlled, it must be measured. If you don't know the current temperature of a reactor, you have absolutely no way to know if you need to add cooling water or steam. Measurement is always the first, vital step in any control system. Technically speaking, measurement is defined as the process of comparing an unknown quantity with a known, predetermined standard value that has been adopted as a unit. So that's just a fancy way of saying, like, comparing the length of a pipe to a standard meter stick, or comparing the pressure inside a tank to a standard atmosphere. The instruments, the meters, the analyzers you're going to use out there on the plant floor, they're simply physical devices designed by engineers to facilitate this exact comparison over and over again, completely dependably. Section 3. Direct versus indirect measurement. In the real world, we basically divide measurement into 2 practical approaches. The first is direct measurement. Imagine you're manufacturing a mechanical part on a metal lathe. You want the part to be a certain size, right? So you literally take a micrometer and measure its physical dimensions. In this case, the meaning of the measurement and the whole purpose of the operation are completely identical. But in chemical processing, we rely heavily on indirect measurement. Consider something like milk pasteurization. The actual purpose of that process is to eliminate bacteria. But obviously, we don't have a reliable, instant way to constantly count microscopic bacteria flying by in a flowing pipe. So instead, we measure the temperature of the milk. We know scientifically that if the milk hits a certain temperature, the bacteria are eliminated, so we measure temperature to infer the bacteria count. The real purpose and the measurement itself are different, but they're reliably related. Section 4. Elements of an instrument. Let's move on and see how this builds. What actually makes up the physical tools that do this critical work? While industrial instruments look incredibly diverse on the outside, almost all of them can be broken down into a standard set of functional elements. Basically, energy flows from the measured medium, goes into the instrument, gets converted along the way, and is ultimately delivered to the observer as usable data. This signal journey happens in 5 general steps. Step 1 is the primary sensing element, which first receives the raw energy from the measured medium. Step 2 is variable conversion. This takes that initial physical signal, say a tiny physical displacement, and converts it into something more useful for us, like a pressure or voltage. Step 3 is variable manipulation, which might amplify or modify that signal. Step 4 is data transmission, actually sending the signal from the loud, dirty process floor all the way to the control room. And finally, step 5 is data presentation, where that data is translated into a readable gauge, a chart, or a digital readout for the human operator to actually look at. And this brilliantly illustrates how those abstract steps map onto a real physical device, the filled system thermometer. The temperature bulb, which is filled with liquid or gas, acts as your primary sensing element, absorbing heat. As it heats up, the fluid inside expands, creating pressure. That pressure is then transmitted through this long capillary tube. So that's your data transmission element. It travels until it reaches a spiral Borden tube that slightly uncoils under that pressure. That's your variable conversion element, literally turning pressure into physical motion. Then linkages and gears manipulate that motion, and finally, a pointer moving across a physical scale serves as your data presentation element. It is just a beautiful, purely mechanical system executing all 5 of those functional steps perfectly. Section 5, the big picture. So zooming back out to the entire chemical plant, all of these instruments we just talked about, they are out there right now, providing a constant stream of process data. This data is fed directly to a central controller, which basically acts as the brain of the whole operation. The controller constantly compares the measured data coming in to the desired set point. If there is a difference between the two, which we call an error, the controller triggers negative feedback. It immediately sends a signal to manipulate a physical variable, like opening up a steam valve or maybe slowing down a pump, all to drive that error right back to 0. This continuous loop, measuring, comparing, adjusting, is exactly what allows the plant to run autonomously, safely, and profitably. But I want to leave you with a really crucial thought. We've established that the entire safety and economic viability of a chemical plant relies entirely on this continuous loop of measurement and control. But if the plant's life depends on these measurements, how do you actually verify your instruments are telling the truth? Think about it. What happens when a sensor degrades over time or suffers from static errors and suddenly starts lying to the controller? That dives straight into the critical world of instrument calibration and performance characteristics, which is exactly what we're going to explore in our next explainer. Keep questioning how things work, and I'll see you then.